Okay, in the last chapter, we have seen that if we have a current carrying wire in magnetic field, there will be a force on this current carrying wire by the magnetic field. And in this chapter, we have seen that if we have a current carrying wire, this current carrying wire introduces magnetic field. So what will be the situation if we have two parallel wires and each of them includes a current? So assuming that this wire A and this wire B, this includes current IA and this includes current IB. So we can see or we can imagine that one of the two wires introduces magnetic field on the other one, and the other one, due to the induced magnetic field and the current inside it, it will introduce a force on it. And by a similar way, the current IB will introduce a magnetic field on the wire A, and due to the magnetic field of the wire B and the current inside the wire A, there will be a force at the wire A. So let us assume that we are talking about the current coming from A reduce magnetic field BA on the wire B, and the wire B has a current IB. So the force, the magnetic force, would be F at B due to A equals the current at B multiplied by its length cross product the magnetic field due to the current at the wire A, BA. So to find the force on a current carrying wire due to a second current carrying wire, first find the field due to the second wire at the side of the first wire. Then find the force on the first wire due to this field. Okay. Now, according to the direction, the magnetic field due to the current at the wire A will be normal to the direction of the current at IB, because these two wires are parallel wires. So in this case, the angle between the magnetic field BA and the current IB is 90 degrees. So the cross product in this case would be proportional to sine 90 degree. So it is proportional to 1. So as a magnitude, the force at B due to A would be IB multiplied by L multiplied by BA multiplied by sine 90 degrees. Now, the magnetic field B due to the wire A at this point would equal mu naught multiplied by the current IA over 2 by this distance, 2 by D. So BA is mu naught IA over 2 by D. So in this case, the force at B due to A would equals mu naught multiplied by the length multiplied by the current at A multiplied by the current at B over 2 by the distance between the two wires D. Okay. Now what is the direction? according to the cross product, I'm saying L cross B, and L in the direction of the current and B in the direction of the magnetic field. So according to the right hand rule, I put my four fingers in the direction of the first vector L, then I rotate my four fingers toward B. My thumb will show you the direction of the force. So the force in this case is attracting the wire B towards the wire A. So if the currents are in parallel and in the same direction, the force between the two parallel wires will be attraction, and vice versa. If the current are in opposite direction, the force between the two wires would be repulsion. Here, the permeability constant mu naught is 4 pi multiplied by 10 to the power minus 7, and L is the length, I is the current, and 2D is the distance. Okay. The force between the currents in parallel wire is the basis for the definition of ampere. How comes? Assume that we have two parallel wires. And the current in each wire is 1 ampere. And the spacing between the two wires is 2 pi. So the force in this case per unit length, assuming that the length is 1 meter, the force per unit length would be mu naught multiplied by 1 ampere multiplied by 1 ampere over 2 pi multiplied by 1 meter. Okay, so mu naught is 4 pi multiplied by 10 to the power minus 7 over 2 pi. So this is actually 2 multiplied by 10 to the power minus 7. And here 1 multiplied by 1 over 1. So this is 1. So if the current in the two wires is 1 ampere and the spacing between the two wires is 1 meter and the length of the wire is 1 meter, so the force between the two wires would be 2 multiplied by 10 to the power minus 7 Newton. So in other words, we can say that ampere, which is a unit of the current, is that the constant current which is maintained in two straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in vacuum would produce on each of these conductors a force of magnitude 2 multiplied by 10 to the power minus 7 Newton per meter of the wire length. So we have introduced here the definition of the ampere or the unit of the current in terms of the unit of power of force Newton and the unit of distance meter. Okay. Here in example, the figure here shows 3 long straight parallel equally spaced wires. So the spacing between them are the same and they are long, so you are going to assume they are infinite with identical current. So the value of the current is the same, either into or out the page. Here A and B are out of the page and C into the page. Okay. Rank the wires according to the magnitude of the force on each due to the currents in the other two wires. The greatest first. Okay. So we want to find the force at each wire, and the greatest force would be the first and then the following one and so on. Alright? Okay. Let us see the force at the wire A. Here we have a force coming from B, which is attraction. And this force is inversely proportional to the distance between them, which is D. Okay? Then the force from C to A, because they are in opposite direction to each other, it will be repulsion. And this force will be proportional to 1 over D. So I have attraction 1 over D and repulsion 1 over 2D. So the attraction is the dominant here, but it is less than 1 over D. Okay? Alright. In the case of the wire B, the force from A to B will be attraction and proportional to 1 over D. And the force from C to B will be repulsion, and it is proportional to 1 over D. So effectively, the force from the wire A and the force from the wire C add together in the same direction at the wire B. And both of them are proportional to 1 over D. So now the force at B is greater than the force at A. Let us see what will be in C. In C, the force between B and C is repulsion, and it is proportional to 1 over D. And the force between C and A is repulsion too, so it would be in the same direction, but it is proportional to 1 over 2D. So here the summation would be 1 over D plus 1 over 2D. Here the summation is 1 over D plus 1 over D. So B is greater than C and C is greater than A. So the arrangement of the forces would be B first, then C, then A. Okay? Alright.